In this video, we're going to look at solving exponential equations. An exponential equation is an equation that has the variable in the exponent. We're going to use that power rule that we talked about. If everything inside of a log is raised to the same power, then we can multiply that power out front of the log. So our steps are going to be to isolate the base. We're going to rewrite the equation so that we have the base by itself on one side with the exponent and then a number on the other side. Then we're going to take the natural log of both sides of the equation. So I'm going to ask that you use ln and not some other log. We're going to apply that to both sides of the equation because when we have a log, then we're allowed to use the power rule for logs. So then we'll use the power rule, and then we'll solve for x, and then we'll use a calculator to approximate our solution. We are still looking for the exact value and also the approximation. Alright, so for the following exponential equations, we want to solve for x using those steps that we just talked about. Before we solve number one using those steps, I want to talk about what we're actually looking for here. So we're looking for 7 to what power is equal to 60. So what we're trying to solve for is what exponent I would put on the 7 to achieve a result of 60. So let's take a guess before we start solving. Okay, so it could be 7 to the power of 1. Well, that would give us 7 as a result, and we want 60 as a result, so that's too small. So let's raise the exponent. What about 7 squared? 7 squared is 49. And we're getting closer to the result of 60 that we want. 7 cubed, well, that's 343. That's way too big. So if I had to take a guess, what exponent would be needed on the 7, I would guess it would be between 2 and 3, probably closer to 2. So let's take a guess, let's say 2.15. Okay, so that's just a guess. Now, as we go through our steps, we should get something really close to that exponent. All right, step number 1, we want to have the base and its exponent equaling a number on the other side. So we want to be really careful with this step. Sometimes we skip this first step and it ruins the rest of the problem. So the first thing that I recommend that you do is to find the exponent. Once you have the exponent, you want to identify the base by looking directly in front. So the base is always the thing that's directly in front of the exponent. Okay? If there was something times that, then 3 would not be part of the base. Okay, so you want to be really careful that you can identify what the base is for that exponent. Once you have the base, the exponent, then you have a number on the other side, then we can go ahead and go on to step 2. For step 2, we are going to apply the natural log to both sides. And I'm going to ask you to always use the natural log. I'm going to ask you to solve all of these equations in terms of the natural log. So when you do your homework and when you're on your homework checks, you're going to see the answers written in terms of natural logs. Okay, so that brings us to step 3. Step 3 says if you look in the logs and everything inside of that log is raised to the same power, then you can multiply that power out front of the log. So natural log of 7 to the x power, everything inside is being raised to the power of x, so we can bring that x out to the front of the log. Okay, step 4, we want to solve for x. So I want to get x by itself. So I want to get rid of what's being multiplied times x, so I'm going to divide both sides by the natural log of 7. So that gives me a final answer of the natural log of 60 divided by the natural log of 7. This is the exact solution. Now we are not required to check our solutions because the domain of an exponential function, what you're allowed to use for an exponent, is all real numbers. So we're not going to have to check our answers here. All answers are acceptable. So we want to have an exact answer, one that we don't get using our calculator, one that we did not round, and we also want an approximation. So this is how we're going to check to see if we're right. We're going to go to Desmos and we're going to type this in and see what we get for an approximation. Okay, so I'm going to go to the natural log, type in 60, come outside of that, we hit divided by, and we'll do the natural log of 7. So I get about 2.104. We'll go ahead and round to the nearest 3 decimal places like we did before. Alright, and that answer is pretty close to what we chose. We guessed about 2.15 and the answer is 2.1, but 2.104. So that is the exponent that would be required approximately to get to 60. Looking at example 2 of exponential equations, we know that we're solving an exponential equation because the variable is in the exponent. So here's the exponent. Our first step is to rewrite the equation so that it is the base raised to an exponent equals a number on the other side. So if that's the exponent, then the base is the number that's directly in front of that. So there's the base and the exponent, and on the other side we have a number. So this step is actually already done for us. Step 2, we want to apply the natural log to both sides of the equation. For step 3, we want to use the power rule. So if everything inside of a log is raised to the same power, then we're going to bring that power out to the front of the log. You want to be careful here that you multiply it using parentheses so that you are algebraically correct. Alright, so our next step is to solve for x. We want to get x by itself on one side. There are a couple of approaches to doing this, but one way is to divide both sides by what's being multiplied times that group. So divide both sides by the natural log of 8. So the natural log of 8s are going to cancel out. And so we're left with the natural log of 40 divided by the natural log of 8 is equal to just 2x minus 1. Alright, so we want to get x by itself, so we need to get rid of that negative 1. So I'm going to add 1 to both sides. So we get natural log of 40 divided by the natural log of 8 plus 1. Remember, we cannot combine those because if you have a fraction, you'd have to give a common denominator. So I'm going to leave them side by side. And then from here, we need to get rid of the 2 that's being multiplied times the x. One way that you could do that would be to divide both sides by 2. But if you do that, you end up with this really ugly complex fraction on the left-hand side. So I'm going to take a slightly different approach. Instead of dividing by 2, I'm going to multiply both sides by 1/2. Right, if you do that, then you do need to distribute the 1/2. So 1/2 times that fraction, top times the top. 1 times the natural log of 40 is the natural log of 40. 2 times the natural log of 8 is 2 times the natural log of 8. Then the 1/2 times the positive 1 gives us a plus 1/2. Here, the 2's would cancel out, and so we're just left with really x. So this would be our exact solution. Right, we'd also like to find an approximation to the nearest 3 decimal places. So for that, I'm going to go to Desmos. All right, so we have the natural log of 40 divided by the natural log of 8. Make sure you come outside of that fraction and do the plus 1/2. So our approximation turns out to be about 2.2 0.74 when I round to the nearest 3 decimal places. Alright, so the challenge here is, can you find the exact value and then also the approximation? So you will be asked for the exact value. Make sure that you can get the exact value with the natural logs in there and then also the approximation. For our third exponential equation example, we want to be really careful with this one about what is our base. So step 1 says we want to isolate the base and its exponent on one side by itself and number on the other. The exponent here is clearly the 2x plus 1. But what is the base for this exponent? If you're not careful, you will say that it's the 9 and the e. But keep in mind that the base is always only the number that's directly in front of the exponent. This is the most common mistake that I see with solving this type of exponential equation. The 9 that's there is not part of the base. Really important. So the 9 is not part of the base, and neither is the -4. So both of those things need to go. Alright, so make sure you're extra careful that you can figure out what the base is. If there's something that's multiplied out front of the base, it is not part of the base. The 9 is not being raised to that exponent. And in fact, the exponent on 9 is a 1. So be really careful that you know what your base is. If you don't do that part correctly, then it doesn't matter what happens with the rest of the steps. Really important. So we need to add the 4 to both sides. So we'll say plus 4 plus 4. So the 4's cancel, and I'm left with, what is that, 17. So now we want to get rid of the 9 that's once again not part of the base. We'll divide both sides by 9. And I am not going to simplify that fraction. Remember that I want an exact answer. I do not want an approximation. If you put that into your calculator, you'll end up getting an approximation. And if you round here, then your final answer will not be exact. So make sure that you don't round and don't use any approximations until the very end. So I'm going to leave that as 17 over 9. All right, step 2 is to apply natural log to both sides of the equation. Now step 3, we can use the power rule to bring the 2x plus 1 out front of that log. Now if you look closely, there's actually an even faster way to accomplish what we want to accomplish, and you'll notice that natural log in e, right, the base of the log and the base of the exponential inside match, so they're going to cancel each other out. So we're left with just 2x plus 1 on the left hand side. That's even faster than that power rule. It's even more powerful. So you want to make sure that if you see natural log in e like that, that you use that inverse property. That's going to make the problem a little bit faster and a little bit nicer and a little bit easier. But on the other side, we still have natural log of 17 over 9. Be careful, sometimes when we cancel out the log on the left side, we have a tendency to also cancel out the log on the right side. But that right hand side doesn't have any properties, it didn't have that inverse property, so we have to leave it as natural log of 17 over 9. Alright, so we want to solve for x. So I'm going to subtract 1 from both sides. I want you to notice that when I do that subtraction, that the input for that log is not changing. I'm not subtracting a 1 from the inside of that log. The inputs are not going to change. The input for a log should never change unless you're using a specific log property. Okay, so that's going to sit on the outside of that log. And then I am going to get rid of the 2 by multiplying both sides by 1/2. Alright, so those cancel and leaves me with just x. I'm going to distribute the 1/2. So I get 1/2 times the natural log of 17 over 9, and then 1/2 times the negative 1. All right, so there's our final exact answer. We can also use Desmos to find that approximation. All right, so I'm going to do 1/2 times natural log, and I'm going to do 17 divided by 9. Remember, I'm keeping my answer exact until the very end, so I haven't rounded anything yet. Subtracting the 1/2, we get negative 0.182 approximately, rounded to the nearest 3 decimal places. All right, so there's our final answer. Example 4 is also an exponential equation. When I look in the exponent, I see that my variable is trapped in that exponent. So we're going to follow our steps for solving an exponential equation. The first step is to isolate the base, its exponent, and get one number by itself on the other side. Now when I look up to my exponent, I look at the number that's directly in front of it, and that only includes the 6. It does not include the 8 that's out front multiplied times that 6. So our goal is to get just the base and an exponent by itself. So we need to get rid of the 8 and the negative 7. These are not part of the base. So that exponent only applies to the 6. All right, so let's get rid of that 7 first. We always do our adding and subtracting first. So I'm going to add 7 to both sides. So the 7's will cancel and I'm left with 16. Now I need to get rid of that 8. And I'm going to do that by doing the opposite of the operation that connects it. So 8 times that, I'm going to divide both sides by 8. Now, if you can simplify this fraction without losing the exact value of the fraction, then that's always a good idea. 16 divided by 8 is 2. So I'm going to go ahead and simplify that to be 2. All right, for step 2, we're going to apply the natural log to both sides. All right, and here we're going to use the power rule. We're going to bring the 3 minus x to be multiplied out front of that log. Once again, we're going to put that into parentheses to make sure that it gets multiplied correctly and we're algebraically correct. For step 4, we want to solve for x. So we want to get this x by itself on one side. This can be solved in a similar approach to what we did on the last problem, but I'm going to use a slightly different approach. And I'm going to take that natural log of 6 and I'm going to multiply it into the parentheses. So I'm going to distribute the natural log of 6. So this is just another way, another approach to solving these types of problems. So that gives me 3 times the natural log of 6. Notice that the 3 on the outside and the 6 on the inside are not getting multiplied together to give me 18. Okay? The input for a log doesn't change when we go through the algebra on these problems. All right, so the next one would be negative x times the natural log of 6. Once again, the 6 is not changing, the x is staying on the outside. All right, so my goal is to get x by itself. So I want to get that totally alone. So we're going to bring all the x terms to one side, numbers on the other. So the only term that has an x in it is this one. So I'm going to move any term that doesn't have an x to join other terms that don't have x's. So that means I'm going to subtract 3 times the natural log of 6 from both sides. All right, so that term cancels on this side. And now I have negative x times the natural log of 6 is equal to natural log of 2 minus 3 times the natural log of 6. All right, we're still trying to get x by itself. So I want to get rid of the negative and also the 6. If we want to think of it like a negative 1 times, then what we can do is divide both sides by the negative 1 and the natural log of 6. So the negative 1's cancel and the natural log of 6 cancels, and I'm left with x is equal to the natural log of 2 minus 3 times the natural log of 6. And I really don't need to write negative 1, I'll just write negative natural log of 6. Alright, so there's our exact solution. Now let's use Desmos to find the approximation. Alright, so that's the natural log of 2 minus 3 times the natural log of 6. Come outside of that. I want to make sure I divide all of that. So I'm going to highlight that. So that's all on top of the fraction minus natural log of 6. Okay, so it looks like our approximation rounded to the nearest 3 decimal places would be 2.613. Alright, so there's our exact and our approximate answers. I think this exponential equation is the most interesting out of all the exponential equations that we've solved so far. Step 1 for an exponential equation is to isolate the base. So we see that the exponent on the left-hand side would apply to the 3. But on the other side, we don't just have a number. We have another exponent with a variable in it, and it also has a base. So this type is a little bit different. But the bases themselves are isolated. So let's move on to step 2. Step 2, I'm going to apply the natural log to both sides. This is an important step. You do not want to skip this step. In your homework and also in the exam, I'd like to see this step. Alright, so number 3, we'll use the power rule to bring those powers out front of the logs. The only reason that we are allowed to bring that power out to the front is because we've already introduced the log. You can't use the power rule for logs if you did not first introduce the logs to both sides. Okay, so there's our power rule, and we have the parentheses out front to make sure that we're algebraically correct. So the work for this really starts in step 4 when we want to solve for x. So I want to get x by itself on one side. So we have a problem. We have an x on both sides, and those x's are trapped inside of the parentheses on both sides. Alright, so let's look at this procedure that we're going to use when we have these two bases isolated on either side. How are we going to solve for x? So we are going to distribute both of the logs into the parentheses. Remember that we want to keep our answer exact until the very end. So I am not going to put natural log of 3 into my calculator and find an approximation. The challenge is to work with the exact values without using your calculator until the very end. Alright, so natural log of 3 times 4x. I'm going to write that as 4x times the natural log of 3. 1 times the natural log of 3 is just natural log of 3. On the right-hand side, I'm going to write that as 2x times the natural log of 7, and then minus 5 times the natural log of 7. You'll notice that when we did the multiplication, that the input for those logs stayed the same. So the 3 and the 7 did not change to become anything else. So our first step was to distribute. Okay, so we distribute the logs into the parentheses. Our next step will be to move the x terms to be on one side, and anything that doesn't have an x term in it, so the non-x terms, we're going to move those to be on the other side. So I'm going to go ahead and I'm going to move this x term to the left side to join this x term. And the natural log of 3, and the natural log of 3 does not have an x in it, so that term is going to move to the right-hand side to join this non-x term. Okay, so in order to move terms around, I'm going to subtract. So minus 2x natural log of 7 and then I'm going to subtract the natural log of 3 from both sides as well. So this cancels out from this side, this cancels out from this side, and these are not like terms. I'm not going to combine them. A big reason is because of the natural log of 3 and the natural log of 7 are not going to change. We're not going to find an approximation. So they're just going to sit side by side as two separate terms. Same thing on the right-hand side. I am not going to combine those. They're just going to sit side by side as two separate terms. Alright, so we distributed the natural log into the parentheses. We have sorted the x terms on one side and the non-x terms on the other side. The next step is kind of the tricky step, and that is that we're going to factor out an x from the x terms. Okay, so we want one x by itself on one side. Right now we have all the x's on one side, but we have two x's. So we're going to take the x out of both of those terms. Okay, when we factor it out, what do we have left over? We'll have 4 times the natural log of 3 minus 2 times the natural log of 7. And the other side doesn't change. Now we have 1x, and it's on the left side, but it's not by itself. So I want to get rid of anything that's being multiplied times that x, so I'm going to divide by that whole entire group on both sides. Okay, anything divided by itself is 1, so that group now goes away. Now I'm left with x is equal to everything that's left on that right-hand side. Alright, so this is our final answer, and it is exact. Now, in addition to that exact answer, which we really want to make sure that we can find, we also would like to find an approximation. So let's put that into our calculator, and Desmos makes this pretty easy. Alright, so I'm going to start at the top. Negative 5 times the natural log of 7 minus the natural log of 3. Highlight all of that so it stays at the top of the fraction. You're going to divide that by 4 times the natural log of 3 minus 2 times the natural log of 7. Alright, so our final answer is approximately negative 21.543 if I round to the nearest 3 decimal places. Now, if your exact answer is in a little bit of a different order, or it looks a little differently than mine, that is fine. When you put it into your calculator, the approximation should be the same. So you say, my answer looks a little different than yours, Miss Spalding. How do I know if it's right? To check to see if your exact answer is right, even though it looks a little different, put it into Desmos. If the approximation is the same as the one that I have, then your exact answer is fine. Okay, it can look a little different than mine, but as long as the approximation in Desmos is the same, then your exact answer is fine. Alright, so our final answer, here's the exact form and also the approximation.